you very much for coming. And you can sit. Just give me a second. So it's my pleasure to introduce Dr. and Professor Zheng. He's an assistant professor with the Department of Electrical Engineering and Computer Science at Wichita State University. Zheng has a very interesting career crossing disciplines several times. So he received his bachelor's degree in electrical engineering and then a master's degree in computer science and engineering. And after that, he continued on to Michigan State University for a PhD degree in electrical engineering. After that, he did a postdoc with the Department of Mechanical and Aerospace Engineering at the University of Virginia. After that, he joined Baker Hughes as a research and development engineer, and then in 2013 he became an assistant professor with Wichita State University, where he is still now. His research interests include dynamic systems and control, electroactive polymers, biomass-inspired underwater robots, control of hydraulic fracturing equipment, and renewable energy systems. So you have a true hybrid between mechanical and electrical state that. His research is more suited for mechanical, although he's doing it with electrical. To some degree meets the mission and vision and objectives of the British Institute for Advanced Systems Engineering. Noteworthy is that Dr. Chen received the Kansas NSF EPS Core First Award in 2015, and a few months back he received the NSF Career Award. So with that, I would like to thank Zheng for being here, and I'm looking forward to your lecture.
Thank you so much for your introduction. So it's my great pleasure to visit UConn as its great campus, and I met many faculty in mechanical, computer science, electrical engineering. I'm pretty impressed by the research and the teaching at the UConn. So today, my topic is bio-inspired underwater robots powered by Electro-Active polymer artificial muscle. So here is outline of my talk. First of all, I will introduce why I want to do using Electro-Active polymer to power the underwater robots. And then I will talk about control-oriented modeling of artificial muscle, and then I'll talk about the modeling of the robotic fish propelled by Electro-Active polymer. And then I move to fabrication side. So I will talk about fabrication of artificial muscle powered pectoral fin, and then I'll talk about development of robotic Manta ray using pectoral fin. And then I'll make a conclusion at the end. So our motivation, basically, nowadays we face a lot of challenge and also a lot of benefits from ocean. So, for example, environmental monitoring. As you said, there's some oil spillage, in the Gulf area. So, how can we monitor the health of the Gulf? How can we monitor the health of the water quality of the river and the lake? So definitely we need some monitoring system, basically to detect the pollution and then to give a warning signs showing that, okay, this area actually is polluted. Don't swim in this area. And then second application is ocean circulation study. As you know, the climate change of our Earth. So basically we want to study how much this kind of climate change impact our environment. So, for example, people using underwater vehicle to study the ocean circulation. That is a long time duration kind of research. Basically, deploy some vehicles in the ocean and then collect the temperature, salinity, those kind of data, and then make a decision that for the policy, basically to eliminate those kind of carbon dioxide emission. And then the third one actually is called seafloor mining. Basically, we have faced a lot of fortune actually in the seafloor. So, for example, if we want to explore some miners in the seafloor. We have to basically send out some underwater vehicle to take a picture of the seafloor and then to do some analysis, what kind of material on the seafloor. So, and then the fourth one actually is called agriculture for fishing farmer. Basically, this basically showing that if the farmer wants to raise some fish in certain area, so before they make decision, actually they have to make sure this area actually is health and then has nutrition in that area. So they need some data actually from the river lake, and then to make sure they can benefit from this kind of fishing farm. Okay, so that's probably also need some data collection, from the underwater. So third one actually is ocean life study. So as you know, some ocean animals basically becomes less and less. So we need to study the living behavior of those kind of ocean animal, and then we want to see if we can send out some kind of underwater, bio-inspired robot to, and then living close to those kind of biological animals. So to collect some data from them, and then they can let the biologists to make a decision. Okay. So as you say, we develop many type of conventional underwater vehicle. Here I just named 3 of them. First one you can see is called a human-occupied vehicle, HOV, occupied vehicle. So this is more like a small summary, right? So people, operator will sit there for a few days and then collect some data, collecting picture, videos. So this kind of vehicle actually is good for short-time underwater exploration. So if you sit in the small summary for a couple of days, it's a lot of fun, right? You can see animal and watch some good environment, underwater environment. But however, if you are sitting there for a couple months, so what's happened? You will be totally bored, right? So it's very boring, to sit there for a couple months. Okay, so that's why we want to develop some unmanned vehicle, and then third one actually is a remote controlled underwater vehicle. So this kind of vehicle basically is connected with a cable, and then people can sit on the surface ship, so they don't need to sit down in underwater environment. So that pretty improves the working condition and also saves the reduce the risk in underwater environment. So that has been done by many companies, the ROV. But still, it's not totally autonomous. So we have to use the cable, connect to it, and then the people have to sit on the surface ship to basically operate this kind of vehicle remotely. So the third one actually is called totally autonomous underwater vehicle. It's AUV, and this kind of vehicle is more like a torpedo. So it contains electric battery and then propeller. So here's a antenna, GPS for GPS and wireless communication. So those kind of vehicle actually can be deployed in ocean for months, and then it will collect all the data and then send to the center to do the data analysis. So those conventional underwater vehicle basically has many advantages. Basically, they can achieve high speed, and then they can have high payload, and then people have already well-developed control strategy. But disadvantage basically the large size and then low maneuverability. For example, this torpedo, if they want to make turning, so they take the large radius to make a turn, and then it is not environmentally friendly. So those propellers basically generate a lot of noise, acoustic noise, basically interfering the marine life animals, and also the propulsion efficiency is low. So compared to the proper propulsion efficiency of the biological animal. So we want to improve the propulsion efficiency and reduce the size. And then people develop some biostyle technology, basically to mimic the swimming behavior of jellyfish, manta ray, and tuna. So basically, those kind of bio-inspired underwater vehicle utilize the biopneumatic design and then to improve the propulsion efficiency and make the robot in compact size. But however, those kind of robotic fish or jellyfish or tuna, this is still using servo motor to generate propulsion. Basically, you can see underneath of this kind of software, there's a linear motor. Basically, can actuate this kind of bear to generate up and down motion. And then this is a rudimentary. Basically, you are using two servo motor to drive two concentric structure. It's a mechanic structure. Using two cables to make it the bed. So this one is tuna fish. This also have a servo motor inside. So I found out, this propulsion efficiency can be improved, but however, they still use servo motor. Basically, servo motor generate rotation as a flapping motion. If you look at biological marine animals, basically most of them using flapping motion to generate thrust. So that's a kind of power transmission. Basically, transmit rotation to flapping for all these robots. There's a kind of mechanical structure to translate the rotation to flapping. So definitely there's energy loss in this kind of power transmission. And also, those kind of robots still generate a lot of noise, mechanical noise. So it's not acoustic and noiseless. So basically, when I look at this kind of robotics, so I want to basically to improve the energy efficiency by using bio-inspired engineering material. Basically, can generate flapping motion naturally, and then it will not have power transmission to translate the rotation to flapping, so it's totally noiseless. And then I want to also basically design, the bio-inspired engineering material help us to design the robot with any kind of shape, so it will improve the efficiency. So, as we know, some researchers develop electroactive polymers for different applications. So electroactive polymers are the polymers whose shape can be changed if we apply electricity to it. So typically the electroactive polymer we call EAP can be divided into two categories. So first in the left figure you can see this is a so-called dielectric elastomer. It's ionic, is electronic EAP. So electronic EAP is driven by the electrostatic force applied to the two electrodes in between. So you can generate large contraction. Okay? So in between is elastomer, rubber-like material, and you can generate large force, but however, it requires high actuation voltage. For this one, typically about 1 kilovolts actuation voltage. So we found out this kind of material is very interesting, but however, it's not useful for underwater application. So second type of EAP we call the ionic EAP, such as conjugate polymer, ionic polymer composite. So here, right move is showing the actuation of IPMC. This is what I fabricated a few years ago at Michigan State. So this strip, we apply about 3 volts square wave signal to it. Basically, it can generate large bending motion. And then this material is driven by the ionic induced swelling effects in the polymer. So basically, it can work under weather conditions. So it can work under underwater environment. So we found out this is a perfect material for robotic fish, and then you can see it naturally generates the bending motion instead of contraction. So here's the actuation mechanism of IPMC. You can see this is a cross-section view of IPMC. It's a 3-layer structure. Inside layer is a lithium ion exchange membrane, and then we coat it with 2 metal electrodes, such as platinum or gold. So if we put IPMC in water, so the positive ion, you can see, it will touch water molecules, and then it can freely move inside. Okay, so this membrane is called ion exchange membrane. So ion can freely move inside. Positive ion can freely move inside. Negative ions are fixed. So if we apply small voltage across IPMC, so what's happened? So those positive ions, such as calcium ion and then cathode ion, will bring water molecules and move to the cathode side. And then in the cathode side, the polymer gets more and more water, so it will swell, volume will increase. And on the outside, the volume will shrink. So eventually, the IPMC bends to the anode side. So this is the typical actuation mechanism of IPMC. So there are many other mechanisms with IPMC. As I said before, it requires low actuation voltage. It's compliant, resilient, compatible to human body. So basically, there are many applications developed in biological, mechanical devices, by micro robots, and then micro nano manipulation systems. So in this research, actually, my major contribution is to develop a control model for the robotic fish propelled by IPMC. So before I developed a model for robotic fish, first step I developed a control model and physics-based and control model for IPMC first. So you can see the existing lot of modeling work. Basically, we can for IPMC, basically we can divide it into 2 parts. The first one we call the physical model. So physical model basically can capture the fundamental physics in IPMC. You can capture the ion transportation, water migration, and then electrostatic interaction in IPMC. So it's very physical and it's accurate. But however, most of these physical models are represented in terms of partial differential equation. So the model actually is very helpful to design and then to simulate the IPMC. But however, it's not practical for real-time control purpose. So we don't have too much computation resources to run the PDE simulation on board. So the second type model we call the empirical model. Basically, the empirical model mostly focuses on the experimental observation between input and output. So we don't care about what's happening inside. We consider it as a black box, consider a system. And then we made the system output and we made the system input. And then we use the system identification method basically to identify those parameters for each case. So basically, it's practical. We come up with a transfer function. This can be used for control design. And but however, it cannot capture the fundamental physics in IPMC. So those identified parameters, they are just a number. They don't have any physical meaning. So if we want to develop different applications with different size, we have to re-identify those kind of parameters in the transfer function. So it's not geometrically scalable. So if we want to develop big fish or small fish, so we have to identify the parameters for the tail case by case. So what I did basically is to bridge the gap between physical model and then empirical model. So this is a model actually is geometrically scalable. So all the parameters in the model they have physical meaning, either physical constant or dimensions. And then it can also capture the fundamental physics in IPMC. So it can capture the ion transportation, electrostatic interaction, and also water migration in IPMC. And also, the model is amenable for model reduction. So based on the physical model, we come up with an infinite dimensional model, and then we need to reduce the model to lower the transfer function so that we can use in our real-time control. And this kind of model actually is amenable for model reduction using parallel expansion series. So I will talk about that later. So our starting point is a physics model developed by NASA in 2000. So you can see here's a cross-section view of the IPMC beam, and then we apply voltage at the one end, so we apply VOT, and then this kind of a small voltage will drive the ion move to the cathode side. So we have this red arrow showing the ion transportation. So, and because this electrodes on the IPMC is not perfectly conductive, so there's a distributed surface resistance along the length. So if you measure voltage at this end, and if you measure voltage at the free tip end, so basically you get different voltage because of the surface resistance. So in Lemonas's model, he developed this ion flux equation, basically captures the ion transportation in IPMC. This C plus, this is the density of the positive ion. This is positive ion can move inside of the polymer. And then the phi is the electric potential, P is the water pressure, and then little v is the free water velocity. And then other parameters are constant. This is constant, and then this is the R, capital R is gas constant, capital T is the temperature. Okay, and then there's electrostatic field equation capturing electrostatic interaction. Capital E is the electric field, capital D is the electric displacement, phi is the electric potential, and then rho is the charge density. Okay, and then there's another equation called law follows the Darcy law. Basically, captures the mean velocity of the free water in terms of electric field, and then the gradients of the water pressure. So we assume that the free water speed is relatively small. So compared to ion transportation, the ion movement. So we assume the little v actually is very, very small. It's close to zero. And then we can simplify this ion flux equation. We write the ion flux equation. So it's a third order nonlinear PDE equation. So you can see here's a nonlinear term showing this gradient of electric field and the electric field. So these are the multiplied together. So this is a nonlinear term. And then we have two linear terms. Okay. So if you want to solve this nonlinear equation, actually it's quite difficult. Okay. The nonlinear PDE equation is not easy to solve analytically, but probably we can solve it mathematically. But in this one, we want to develop an analytical solution for PDE. So we have to make the simplification. So we assume we can cancel this kind of nonlinear term. So if we cancel this kind of nonlinear term, so this PDE equation becomes linear second order PDE equation. So we can use this linear PDE equation to get an analytical solution. But however, we have to make this cancellation under some kind of assumption. So that assumption is like this nonlinear term is really relatively small compared to this linear term. Okay, so under this condition that we can cancel out this nonlinear term. Otherwise, we cannot just delete it, right? So by looking at these two terms, if we compare these two terms, basically finally we can see that if we want to cancel this term, we must satisfy this condition that the charge density actually is much less than negative ion density. So that means, not all the positive ion are transported. So only small amount of positive ion are transported, so that we can cancel out this nonlinear term. But however, if you apply extreme high voltage to the IPMC, basically a large amount of positive ion will move to the cathode side. So which means we cannot ignore this kind of nonlinear term. So this cancellation is based on the assumption that we apply small actuation voltage to the IPMC, and only small amount of positive ion are transported. Okay. So under this condition, we we can simplify simplify this ion transport equation to a linear second-order PDE equation. So in terms of charge density, and then this block parameters we call the capital K. This is a constant. So we have this second-order PDE ion transport equation in terms of charge density. And then to solve this linear PDE equation, we have to know what's the boundary condition. The boundary condition is that first one is ion flux is equal to 0 as a boundary. This assumes that the no ion leak to the outside of the polymer. And the second one is the prescribed potential as a electro-metal polymer interface. So the voltage applied to the IPMC as it is fixed at the time. But however, it's not fixed along the length. So that's why we introduce this circuit model, power transmission line circuit model, to capture the distributed surface resistance effect. So this is just showing one unit of this circuit model. So you can see the R1, R2 are the distributed surface resistance in length direction and then in thickness direction. And this RP is a distributed polymer DC resistance in polymer. And then inside of this block, red box, this is dynamics governed by ion transportation equation. This block basically is governed by second order linear PDE. So it's very challenging to solve this PDE equation, with this kind of integral differential equation serving as boundary condition. So here's the electric potential along the length. Basically, you can see it's function of the input voltage we apply at the time, and also it's a function of the length in the length, and also this IS is the surface current, distributed surface current, and this IP is a distributed DC current. Okay. So it's very challenging to solve this kind of PDE equation with this kind of boundary condition. And we took a system perspective to look at this modeling work. So we consider this IPMC as a whole system. We really care about is the relationship between input and output. The input is voltage, output is either bending displacement or actuation current. So, and then the connection of this input output to the PDE are those equations. So we apply voltage at the time. So electrical potential difference at the time is input voltage. And then we collect the current at the time. So the surface current at the time is equal to the actuation voltage. And then this is a distributed electrical potential along the length. And then the last one basically showing the electromechanical coupling effects, showing that the induced stress is proportional to the charge density. So after we consider these connections, we need to solve the PDE equations. So how to solve it? So we use the Laplace transform. We convert the linear PDE from time domain to Laplace domain by taking Laplace transform, and then we get this Laplace transform in terms of S, and also in terms of Z. Z is a unit in thickness direction. And then we can solve this second order equation, order equation, and then get this generic equation for charge density, electric field, and the electric potential. So you can see there's a hyperbolic linear function, sin h, and cosine h function, and A1, A2, C1, C2, and the beta of S are all transfer function in terms of S, and also in terms of physical parameter and dimension. And then they're also proportional to the input voltage V of S. So finally, we get two types of models. First one is called impedance model, relating input voltage to output current. So So you can see this is an infinite dimensional transfunction. We have a square root transfunction, square root function, and then hyperbolic tangent edge function. So this is an infinite dimensional transfunction. We want to reduce this kind of infinite dimensional to finite dimensional. So we use Taylor expansion. Basically, can reduce this kind of transfunction to lower the transfunction. And the second model we developed is actuation model relating output displacement to input voltage. So you can see this is also infinite dimensional transfunction. We can also reduce it to lower the transfunction using Taylor expansion theory. So we want to validate this model. Basically, we develop a mathematical model, and we want to see if this model is accurate or not. So we have a validated impedance model and actuation model. On the left figure, we show this body plot of impedance, the magnitude, phase shift versus different frequency. So you can see the model. The red dashed line is a model with simulation without surface resistance. So actually, this black line with dot are the experimental data. And then blue line shows a model with surface resistance. So we can see this the model without surface resistance is worse than the model with surface resistance. So actually, by considering the discrete surface resistance, we actually can improve the model prediction. So that's probably one of my major contribution in this kind of model work. Basically, I consider the distributed surface resistance on the electrode. So second figure shows the polyplot of the actuation model. So you can see those blue dots are the experimental data, and then the black dash, red dash line are simulation data with original model. So you can predict it fits the experimental data pretty well, and then the black solid line shows the simulation data with reduced model. So you can see both reduced model and original model can predict experimental data, fits the experimental data pretty well in low frequency range. But however, at high frequency range, this is some big errors. So, but however, this material actually only responds to low actuation voltage. So which means low frequency voltage. So which means this reduced model actually is accurate in low frequency range. So we can use this reduced model for control design. So here we design and implement model-based actuation control for IPMC. So here's the actuation control design. So P of S is a reduced model, the lower the transfunction, and then there's data A. Basically, it's a modeling error due to the model reduction, and then also some other unmodeled dynamics. And then this data A actually is bounded. And we want to design K of S, it's called actuation control, to minimize the effects of disturbance and also try to minimize the control effort. So basically, the actuation control design is trying to minimize the actuation norm between D1, D2, and Z1, Z2. So we follow the standard actuation control design and come up with this K of S, actuation controller, and we implement this controller in real time to track the multi-frequency references. So here's the experimental results. The blue line is the element, and the red dash line is the reference. So we can see this actually can follow the reference pretty well, and then the tracking error is small. So after we get the practical and then physical model for IPMC, the second step we want to develop speed model for robotic fish. So you see how much voltage we need to apply to the fish tail, and and then how much speed the fish can swim. So here's a robotic fish developed by Mr. Shankara, Michigan State. He was a master student. So you can see this is a small size robotic fish, about 18 centimeter long, and then we will have electronics battery on board. This is an antenna for TV communication. So here's a fish tail. The black being is IPMC, and then we attach a passive passive thing at the end to improve the thrust. So you can see the fish can swim very quickly. There are no gears, no motors, and then the speed can reach about 2 centimeters per second. It's about 1/4, 4 lengths per second, and it can swim more like a fish. And so this is a small size. So we want to develop some application for this kind of robotic fish. So before we develop application for robotic fish, so first step we want to understand the model, the dynamics of the robotic fish, and then develop a model for this kind of robotic fish prepared by IPMC. So our starting point is Lighthill theory. So Lighthill theory tells that the drag force, capital D, is function of the drag coefficient, and then density of water. Capital U is the mean velocity of the fish, U square, and then S is the wetted surface. So this basically is come up with a drag force to prevent the fish to swim. Second force is called thrust force. Thrust force basically generated by the IPMC tail. If you have a oscillating tail, so this thrust force is a function of the little m is the virtual mass per unit length, and then it's a function of water density, and then it's also a function of this so-called bending velocity at the end. So little w is the bending displacement of the tail. So this partial w over partial t basically captures the velocity of the bending tail. And then there's another term is related to the bending slope at the end of the tail. So if you take partial z over partial w over partial z, you get a slope. So the thrust force actually is a function of these two parts. Basically, this one basically generates the positive component, and then this part basically generates a negative component. So capital U basically is the mean velocity of the fish. So at the steady state, so the drag force is balanced by the thrust force. So if D is equal to capital T, mean value of capital T, and we can solve these two equations to get mean velocity of the fish. And then this mean velocity of fish basically relates to the bending displacement at the end of the tail, and also the slope at the end of the tail. So basically we can zoom in to the dynamics of the fish tail. So if we can get the actuation model of the fish tail, basically we can put it into this equation. We can solve for the mean velocity. So we focus on the actuation model of the tail. So here's a cross-section view of the hybrid tail. So the black being basically is active IPMC, and then we have this light blue being is a passive fin, formula at the end of the IPMC. So there's a distributed fluid dynamics force acting on the black being and also on the passive thing. So basically, we can use first order beam dynamics equation to capture the vibration of this hybrid beam, and we incorporate those actuation facts. Basically, those actuation, the bending moment generated along the beam are distributed, so we can decouple this kind of distributed moment into distributed force plus a concentrated moment. And then for the loading effects, basically we can incorporate those hydrodynamic force acting on the passive fin into two kind of components. One is a concentrated force acting at this joint, and another one is a bending moment acting at this joint. So we can solve this coupled equation and then get a two transfer function. First one relates the slope of the tail to the input voltage. Second transfer function relates output displacement to the input voltage. So after we get this 3D, H3D and H3, so the transfer function we can put into the Lighthill series and get the mean velocity of the fish. So this J, so omega is the flapping frequency. AM is the voltage amplitude applied to the IPMC, and other parameters are either physical parameters or dimensions. So we want to validate the geometric scalability of this model. So we designed three different tails, tail A, tail B, and tail C, with different dimensions, either IPMC dimension or passive fin dimension. And then we validate them, identify some parameter like Pectoral CD, some parameters in this model using one set of data. So this figure shows very good fitting between model prediction and then experimental data. And then we use the same kind of parameter to predict the speed with different tail. So to validate the geometric stability of the model. So we can see those models can predict experimental data pretty well with different fish tail. And also in each figure, you can see just the optimal operation frequency, flapping frequency, so that the fish can reach optimal speed, the fastest speed. And also the speed actually goes down if we increase frequency. The reason is that this IPMC is the dynamics of IPMC is a low pass field, so it cannot respond to high frequency signals. So that's why the bending displacement decrease as we increase frequency. So after we've done the modeling of the robotic fish, so we want to develop some other type of robotic underwater robots using IPMC. So here's two movies showing the swimming of a manta ray. So manta ray actually are a large species of ray. They can swim long distance with low energy consumption, and you can also have very high maneuverability, make a quick turning, and also the span wise of the manta ray is about 7 meters. So we want to develop this kind of robotic manta ray actually using smart material. So as you can see, in this manta ray actually they use twisting coupled with flapping motion on the pectoral fin to generate high efficient propulsion. So we want to develop, pectoral fin basically can generate both twisting and then flapping motion. So as first step, I used the micro-fabrication technology to develop IPMC powered pectoral fin. So the idea is we want to develop a membrane basically has different active areas. Those active areas are isolated. So if we apply different voltage to the active areas, and then we can generate complex deformation of the membrane. So here's the fabrication process. First, we use plasma etching to thin down the passive area, so to make sure the passive area is flexible and then doesn't constrain the bending of the active area. And then we use lithography approach to pattern the naphthalene membrane, and then we can perform selective electroplating, basically can deposit metal on the active area other than passive area. So here's a movie showing the actuation of pectoral. So this thing is about 1 inch by 1 inch, and then we apply 3 different voltage to the 3 different active areas with about 6-degree phase shift. So you can see this membrane actually can generate both twisting motion and also flapping motion. So second approach, we want to use model-based fabrication technique. Basically, we want to make sure the passive area we can choose soft material other than just naphthalene. Naphthalene membrane is quite rigid, not stretchable. So that's why we developed this kind of model-based, molding-based fabrication process. Basically, we fabricate IPMC first, and then we make a mold. Have a different area for the IPMC, and then we can mold this kind of IPMCs into this mold, and then we using PDMS to cascade this kind of membrane. And then finally, we get this IPMCs pectoral using this molding process. So here's a twisting motion generated by the IPMC pectoral in air, and then here's a movie showing the actuation of this IPMC pectoral underwater. So for comparison, we developed 2 different fabrication techniques. Basically, based on the micro-fabrication technology and also based on the PDMS molding technique. So for micro-fabrication technology, so we actually can fabricate macro and meso size IPMC pectoral, and then we can shrink down to 100 micrometer. So this one is that we cannot select the material in the passive area. So we cannot choose the softer material in the passive area. And also it's time consuming, and then it's quite expensive. But the second method actually, you can develop large size of the pectoral, and we're able to choose the softer material in the passive area, and then the cost is low, and then this fabrication process is quite easy. So this one is we are able to fabricate in micro metal size, and it's also incapable of batch production as well. So for this robotic mandatory application, so definitely we don't want to fabricate very small size of robotic mandatory in micrometer. So it's still in centimeter size. So we can use PDMS modeling process to fabricate pectoral. So here's one example. So we have these 4 IPMCs bounded by PDMS soft membrane, and then we put the electronics on board, and then let it swim. Okay. So actually, this robot mandatory has only 55 grams, and then maximum speed can reach up to 0.05 body length per second. It's quite slow at this moment, but if we improve the power, basically increase the power, basically we are able to make it swim faster. So for this small size of battery, the power consumption is less than 1 watt. So in order to simplify the control strategy, instead of using 4 IPMC on each pectoral, we use just 1 IPMC at the leading edge, and then on the trailing edge we have this PDMS soft membrane. So basically, this design showing that this leading edge actually generated by the motion, flat motion generated by the IPMC, and the leading edge will make the trailing edge follow with certain kind of phase shift. So you can see there's very little twisting on the membrane,
So if we increase the frequency, actually we can get a little bit larger twisting. But however, the IPMC can only respond to low flapping frequency. So that's why the twisting angle is quite small. However, it still can make the manta ray to swim. That's a swimming test. So the size is about 20 centimeter wide and then 10 centimeter long. It's quite small. It's quite small. So the last project actually in this area is Buoyancy voice control device. So as I showed before, we can make very good 2D maneuvering, like turning and swing forward. But however, the depth control of the robot is quite difficult. So in this project, I use this so-called IPMC to produce gas, hydrogen and oxygen gases, so that it can increase the volume of the voice control device underwater. So here's a movie showing the gas generation. So after we apply about 5 volts, basically we can generate a lot of gas. And we flatten all the gas in a gas chamber here, and then can increase the volume of the device. And we have this solenoid valve to release gas. Basically, we can decrease the gas volume so that it gets negative buoyant. So here's an open loop test of this voice control device. So at the beginning, basically we open the solenoid valve and then let the water get into the device, and this robot sinks down to the bottom. And then after 3 minutes, we close this. We close the valve, and then we generate gas using IPMC. So after 3 minutes, it pops up to the surface. So this just shows the open loop test. So eventually, we want to develop a closed loop control to maintain this kind of device at a certain level, so that we can put this kind of device into underwater vehicle or underwater robot. So it's low power consumption, low noise, it's compact size. So make conclusion. So in this research, I have developed controlling model for IPMC actuator, and developed a speed model of the robotic fish using IPMC as a fish muscle. And I also developed 2 types of fabrication processes to fabricate the pectoral fin to generate the twisting motion coupled with flapping motion. And also develop a robotic manta ray using this kind of pectoral fin. Here's a list of references. And this research was supported by NCF and OR. So I want to thank my former PhD advisor, Dr. Robotie, and then my former collaborators at the Michigan State, Shetler, Mr. Shetler, and then Mr. Demo. And also want to thank my postdoc advisor, former postdoc advisor, Dr. Phil Parsons at Western Virginia. And also my colleague, Nick. Okay.
So let's thank our speaker. And we're over time, but we'll save a few minutes for questions if you have any.
What make it generate gases in the Polymer slides that you showed? When you apply the voltage?
Yeah, I apply voltage to the IPMC. So IPMC basically is called the ion chain. Inside is ion chain membrane, and we coat it with the vacuum electrode. So if we apply both smaller than 1 or 2 volt, basically this kind of electricity and decouple the water molecules into hydrogen gas and oxygen gas. And then the platinum electrode actually act as a catalyst, basically impel the to water split, help the water split.
So I have this question. I'm working on more biomedical applications. I just wondered, so if this, first of all, what is actually this polymer, and what is made of? The polymer, and is any work that's looking at how biocompatible this polymer is?
Yeah. This polymer actually inside polymer is naphthalene exchange membrane. Naphthalene is ion exchange membrane. Basically, you can purchase from DuPont. Basically, typically people use this ion exchange membrane for fuel cell. Okay, so the PEM membrane, so you can purchase this kind of membrane. And then we coat it with platinum electrode. So platinum actually is a biocompatible to water. So, and then the naphthalene membrane itself actually is also very stable in the
because working under the water.
Yeah, it can work under wet conditions. So there are some applications where like using this kind of IPMC to develop some micro-fabrication to grab the cell, so something like in micro size. So.
And you always need to have that encapsulated.
Yeah, you need to have some essentially using pyridine, so those kind of polymers. This is polyene actually is compatible. So I think don't time did some work on the packaging those items using deposit PV CVD deposition deposit
So how far are you from artificial birds? Short artificial fish. So can you deploy? Can you use the same technology to develop artificial birds that can fly?
Yeah. So for artificial robotic bird, right? So basically, the advantage of using IPMC basically is because it can work on wet conditions. So if you want to develop robotic bird, actually, there are some other actuators. For example, the Electro-Active or PCT, piezo, here basically can generate faster flapping motion. For this IPMC, basically it cannot respond to high flapping frequency. So that's why we use the in underwater environment.
And what's the speed that you can hope to get the best ion polymer? What's the maximum speed that you can
Maximum flapping frequency?
Yeah.
So as we said, say in the previous slides, the dynamics of IPMC. See, so this is the cutoff frequency. Probably this is the hertz. So 1, 2, 3, 4 hertz. So this is on the water environment. But if you operate in air, probably it's about 7 hertz, the cutoff frequency. So this is about 3 hertz.
Okay, that's enough. I think we're going to kick us out here. Thank you very much.
Yeah, I have to lunch. Oh, yeah.
Yeah.
So yeah, let me show you.
Oh yeah, last year. Oh, yeah.
They said you want to go for lunch. Yeah, I'm going to. I'm kind of get going to that. Oh, let's go. Time. What is your Chen? So we have a double with one. We've got yeah, I think it just I wouldn't worry about the I thought you might use it up like that.
Do you know about the status of these weapons? I was just going to kind of wait until all the people exited, but I'm assuming you guys are more than welcome to take cool. As well as the tea, probably. I would say just go for it. So guys, if anybody wants a muffin, I think that these were from